Hello again. My name is Masood Olia, and I'm a professor in College of Engineering, Mechanical Engineering Department. And I'm back with another video, hopefully a short one, related to dynamics, and in this case, actually, kinetics of particles using second law. So here in this problem, I have a ramp whose profile is given by this exponential function, 0.02 e to the power x. And this block or sack, whatever you want to call it, has a mass of 8 kilograms. As it goes through this ramp, when it reaches this position, x equals 0, which corresponds to a y of 0.2, actually, you could see that here from the equation. It has a speed of 1.5 meters per second. At that instant, I want to find the normal force exerted by this ramp on this object, the 8 kilogram object, and also find the rate of increase in speed. By the way, we are assuming that there is no friction, so the ramp is very smooth. So what would be the normal force, and what would be the rate of increase in speed? Now, rate of increase in speed is actually the tangential acceleration, which is defined as dv dt, or the derivative of velocity, v dot. So we are trying to find n and this a sub t. That's the objective. OK, so as is the case for all the kinetics problems, you need to draw a free body diagram. So our free body diagram is going to be at this exact location where x is 0 and y is 0.2. So let me draw my free body diagram here. So remember now, this is our tangential axis, and this is our normal axis pointing toward the center of curvature. So let me start with the unknown force, normal force that we are trying to find, n, perpendicular to what? To this surface, right? And then we have obviously the weight of this object, which is 8 kilograms times 9.81, or 8g. That's going to be in newtons. Now, you have to realize that in order for me to break these forces, the forces into normal and tangential direction, first of all, the reason I'm using nt as opposed to xy is obvious that this is a curved path. So we have to use the n and t. We cannot, it doesn't make sense to use xy coordinate system. OK, so the way we do this is we have to figure out this angle, theta, which is the same as this angle right here. So that angle has to be determined by calculus and using the profile of this path. You guys know that this angle, which is basically the tangent to the tangent of the slope of the tangent line, is actually y prime. So go ahead and take the derivative of this guy, which would be 0.2 e to the power x, right? So because the derivative of x is 1. And as we plug in the x equals 0, that becomes 0.2. So then this is the derivative, and derivative is nothing but tangent of the angle. So if tangent of the angle is 0.2 and we take the inverse tan, that comes out to be 11.31 degrees roughly. So we know now this angle is about 11 degrees or so. OK, so that's one thing we need. The other thing we need is actually what is the center of curvature of this path, or what is the radius of curvature of the path. You guys know from what you've seen in the class that rho can be determined by calculus as well. And that's 1 plus y prime squared, the whole thing raised to power 3/2 divided by second derivative of y, take the absolute value. We already determined y prime, by the way. Let's go ahead and find y double prime. Y double prime actually happens to be the same thing again as you take the derivative. And again, at x equals 0, that becomes also 0.2. So go ahead and plug in to this equation. Denominator is y double prime 0.2. Absolute value is still would be 0.2. 1 plus 0.2 squared, then the whole thing raised to power 3/2. I have the number here for you. That should give you a radius of curvature of about 5.3. Can be a little bit more accurate, 5.303, and that's in meters. Now, why do I need radius of curvature? Because I need to figure out what is the centripetal acceleration, normal acceleration here. Normal acceleration, as you guys know, is v squared over rho. We already have this speed, 1.5 meters per second squared divided by this radius of curvature, right? So that comes out to be very small acceleration, very small acceleration. So if this was a ride in an amusement park, it would be very, very unexciting ride. Because look, the acceleration is not even 1 meters per second squared. It's not even g. It's not even 10 meters per second squared. So not much is going on. Anyways, ready to apply the equation of motion in the normal direction. Sum of the forces in the normal equal mass times normal acceleration. Now that we have the normal acceleration, this is the positive direction. So we go ahead and try to break this, the weight, which is 8 times 9.81, along the normal axis. So that becomes the cosine. So times cosine of this angle, 11.31, right? That's it. Equal mass, which is 8 kilograms, times this normal acceleration that I just determined for you. There we go. So go ahead and solve for n. N happens to be about 80.4 newtons. The unit of forces in the metric system is newtons. Now, what about the rate of change of speed, tangential acceleration? Apply the equation of motion in the tangential direction. Remember, there is no friction. If there was friction, guys, then you need to put the friction force right here. And you need to know what is the coefficient of kinetic friction. But look, this is my positive direction. So the only force has component along the tangential axis is the weight, 8 times 9.81 times sine theta, or sine 11.31. And that's equal to mass 8 times the unknown tangential acceleration. So if we solve for a sub t, we should get 1.92 meters per second squared. And that is the rate of change of speed, which means it's increasing at this rate at that particular instant. Remember, these numbers are not fixed numbers. They are changing. Normal force is changing because the angle is changing, as well as the tangential acceleration is changing. Now, if you want the total acceleration, you could find the total acceleration. This is the tangential component. This is the normal component. And the total acceleration would be something like this. You have an here, which is very small. A sub t is much larger. So you would get a component like that. So this is it for this particular video. And I'll hopefully come back with more exciting videos later on. Thank you for watching and listening.